Northwest. And Professor Razeghi is recording the meeting, I think, because we actually are not recording it, by the way. So I'm going to ask Professor Ekmel Özbay to introduce her, and then we are going to have her talk about her latest interests and guide us about some future in material science, I guess. And I'm going to ask this again. Please turn on your cameras. That was a special request, Professor Razeghi, and it would be great if, unless you have a very good reason for not doing so, please do turn on your cameras. Thank you.
Okay, I will say it in Turkish. Arkadaşlar kamera açalım. Bu özellikle Profesör Razeghi'nin ricası. Ne kadar çok kişi açarsa seviniriz şeyde. All right. So it's a pleasure and honor to host Professor Razeghi, who had been a very good friend. I don't know how many years. But we even call each other with name, Manish, in that sense. So I will just, read it from the bio, but I will also try to tell as much as I remember with our interaction with her. So she received her PhD from, this is French, I cannot pronounce, but from University of Paris, let's say, in 1980. Then she joined Northwestern University as a Walter Murphy Professor and Director of the Center for Quantum Devices for 1991, where she created the undergraduate and graduate program in solid-state engineering. She has authored and co-authored, believe it or not, more than 1,000 papers, more than 34 chapters and 20 books, including the textbooks, Technology of Quantum Devices, and a number of them related to her research topics. So her current research interest is nanoscale operating quantum devices. She's a fellow of MRS, everything you can come up with, IOP, IEEE, APS, SPIE, OSA, fellow and life member of Society of Women Engineers, fellow of the International Engineering Consortium. She also received the IBM Europe Science and Technology Prize in 1987, the Achievement Award from the SWE in 1995, the Bun Shah Award in 2004, IBM Faculty Award in 2013, and Jan Czochralski, at least I know how to pronounce that name, Czochralski Gold Medal in 2006. The 2018 Benjamin Franklin Medal in Electrical Engineering, and many other Best Paper Awards. She's a directed Life Fellow for SWE, IEEE, and MRS. So again, Manish, thanks for accepting our invitation, and we are looking forward to your talk, which I'm sure will be very exciting.
Okay, thanks a lot. Again, I have to say that Turkey is my favorite country because they are great scientists. And you have to know that my best, really a student at Northwestern is from Turkey. And we have one of your students at the same time, professor in our the Bakore Aydin, and we have at the same time the professor, the John Byram, that you know that, all of you. But
I know both of them very nice.
Absolutely. But all of you have to know that the Professor Ekmel, near 30 years, at least I know him and my student know him. Why? Because due to the problem of aluminum gallium nitride, the detector, the things that I'm going to say. Today, I have to say the subject that I choose for you is, first of all, that's a subject for all of you. You have to know that is supported by somebody, the great scientist, Dr. Ali Said at the Air Force, that he is a great scientist and material scientist at the same time. And independent, he is looking for the best group around the world. And the subject that you can see, that is the subject that he tried to encourage and to support us. So let me to explain to you first of all, the following. That exactly the outline, again, I'm going to give an introduction and at the same time to explain why gallium oxide and what is the really future for that. First of all, I would like to start to tell you the secret of science, as you know, is in the periodic table. And the most important part, if we can understand the structure of the really hydrogen, that is 1 electron and 1 proton, we can understand the structure of world. And the most important achievement of the last century, it was a little understanding the structure of atom thanks to quantum mechanics. And when you look inside of the atom of hydrogen, and if you look at electron, we say that negative charge when it's running, creating electric field. The spin of electron around that create the magnetic field. Together, they are giving the electromagnetic wave that we know, and that we say that this electron can have the energy to move, and this energy come from what? From the movement of the electron and the movement of the nucleus. This movement gives the energy, and this energy, it can absorb by the electron to go higher energy level. That's the basic of the detection, and coming back to give again this energy as a photon, that is the basic of the emission. So as you can see, if we understand the structure of the really this atom of hydrogen, we can understand the basic of all of the most important, the active element that is transistor, lasers, and detector. Emission, detection, and at the same time, the analysis of the data. So if we can understand that, everything else, it becomes much easier, especially for the scientists and the Bachelor of Science, the student, and at the same time for all of us, when we are coming again for the semiconductor area. And by that, as you can you know, we can go from the gamma X up to the far infrared and the above the terahertz. But unfortunately, our eyes can see only a small part of the periodic table of the electromagnetic wave. It means that visible part between 400 to 700 nanometer. So we are curious in order to be sure to have access on the extreme. And for that, when we say semiconductor, in the past, all of us, we knew that silicon, carbon, germanium, colon 4. But what's the problem of the colon 4? They are covalent, perfect, but they are in direct gap, and at the same time, they have diamond structure. Silicon, we know that is the best, I said, that gift of God for the electronic device. Why? Because we have for the silicon 2 material, silicon carbide and silicon nitride dielectric for the passivation, that is perfect lattice match to silicon. So make that really for many different applications excellent, excellent. And at the present time, one of my students, again, the David Haydari, that he's doing his PhD at this time at Stanford, and he is online, and his PhD is how to make silicon under pressure to change the energy cap and to make laser from emitter from the silicon. And they are doing it. But thanks God, it still is, we have 3.5. So on the other hand, I want to attract the attention of all of you on carbon. Carbon is the unique element in the periodic table, that the unique structure, that the bonding of the different carbon atom together can come to give us the diamond, that is the hardest material, and at the same time, with the only bonding of the carbon to carbon, can give the graphene, that is the zero band gap. And already we had 2 Nobel Prize, and I'm sure 100% is going to have the other, and I'm expecting maybe that even the high TC superconductivity come from again, one of the carbon based material. But that again, another problem, is not very simple, easy, in order to make exactly the things that we need, the high power lasers, high power high performance detector at different wavelength, etc. So that again, but that is future. We don't know, because at this time there are many, they are working on the carbon, and graphene is a zero band gap, but to change under the different format in order to make even the lasers from the carbon, from graphene. So that is something that I want to attract the attention of everybody, that is future. But one of another possibility that we have here is the colon 3 and colon 5. Colon 3, colon 5, they are direct bond gap, they are covalent, but at the same time, most of them zinc blend. So at the present time, it is, and is continue to say that silicon colon 4 is the food, but 3,5 is the salt of the food. We need them. And we need them, we know that since 30, 40 years is going to continue, and you have to know that in 40, 50, 60 years in future, when I'm not there, and some of the students and all of you are there, you have to know that still they are going to be the perfect material for the difference, the lasers and detector from the different. But one of the beauty of the understanding of the structure of atom due to the quantum mechanics, we understood now that any material with the monolayer can have the semiconductor behavior. So one of again, the talk that I would like to give to you, message to you, is oxide. You know that the high TC superconductivity, after 3 Nobel Prize that they mentioned that is impossible, after that Muller and Vendors, they came with the material of the chemists to show that no, with the oxide, yttrium, barium, and all of the EBQ, they tried to demonstrate, no, we can have the high TC superconductivity, and they got Nobel Prize. I would like to show you now today not only 3,5, but 3,6, how can be useful for some of the application that the 3,5 cannot do. And especially the reason that I insist on that is more for the coronavirus. How to come with this material to have a kind of LED and the detector in order to be sure that we can detect some of because all of this virus, as you know, they are a kind of the protein molecule. And all of this protein molecule, they have the fluorescence that some of them is at very deep UV that we cannot have with the 3,5. So that is my message today. So for some of you, you have to know that you are not in the world of the semiconductor. The semiconductor today, it is, and is continue that with any format, we need, again, as I mentioned, we need the detection, we need the emission, and we need at the same time the electronic. It means that the transistor to manage with the photon. So in anywhere from the food, energy, transportation, communication, everything that you can see, we have and we need one, at least the semiconductor device, and I'm telling that quantum, and I'm going to tell you why. So what we can do, again, as you can see here, with the colon as an example 3,5 or 6,2, or say, we can do atomic and gap engineering, and to make exactly the crystal that the nature didn't give us. But we can make artificially, and by that we can come up with the electronic and optoelectronic devices that from deep UV, X-ray, gamma, up to the above terahertz. Now, what was the most important achievement of the last century in order that we can do that? One is the invention and the fabrication of the substrate. And Chokralski, and that Dr. Ekmel that you get, Chokralski, he was
I should correct you, Chokralski.
Absolutely.
How many times I try to pronounce this? Yeah,
because he is the Polish.
I know the story.
Exactly. He was the 100 years ago, the great chemist that he was in order to put his pen inside the ink, he put in the molten zinc. And that it was a starting of the crystal growth. After that, of course, the bell after week. And now, one of the important, because everything that we do with the semiconductor thin film, we need the support, and the support is the substrate. So it was here that now we can have in many different cases to have the substrate. And you are going to see that why is important, and I'm putting that in the case of the gallium oxide. And if we compare with the gallium nitride, and after that we have the substrate is epitaxy. That again, the last the century we came with the LPE, vapor phase epitaxy, MBE, MOCVD, with the different kind of the deposition, epitaxy, atom by atom. And one another thing, it was the photolithography. Because putting that together, following the nature say that if we use bulk materials such as silicon, gallium arsenide, we have the energy as function of density of state is parabolic. So the device is not going to be very efficient. But if we use epitaxy, now we can do the quantum well. And in this case, density of a state as function of energy, we have one-dimensional confinement, we can have better performance of the optoelectronic or quantum device. But now if we use at the same time the photolithography, in this case, we can come up with the quantum wire or quantum dots. Quantum wire lock the molecule, quantum wire lock the atom, exactly artificial atom. In this case, we can have much better performance and eliminate the waste energy of the phonon, etc. But unfortunately, that is not, God didn't give us everything. God, only the perfection is for God himself, not for us, but give us some problem that we are mimicking the nature and inspiring by the nature. Because all of us, the basic 5 human sense, all of that we understood now, that is based on the quantum, the quantum device and the small dimension. And that there are million and million sensors for the other example, our eyes or ear, everything. And all of the information is go with the little energy, only 37 milli-electron volt, through all of the vein, and to move all of the information to go to the brain, and brain does all of the signal processing, cognition, everything like a computer. So that is more based on the electronic, and that is more based on the photonic. So we try to learn that, and by that we come again to create artificial, again, eyes, and at the same time the different laser and detector. So it was after my PhD at Orsay University in Paris, at Orsay, after I was the nuclear physicist and at the same time solid state physicist, that I was doing the phase transition in the lead phosphate, that there is a kind of perovskite, and that with the electron spin resonance, and to use paramagnetic ion as a probe for the phase transition. So it was more theory, calculation, everything, and I didn't have really any background knowledge about the semiconductor. So, but everybody was coming, said that, okay, it's very nice physics, very nice, but what's the application? So that it was after my science doctorate at Orsay, side by side, it was the Central Research Lab of Thomson. I went there to become familiar with the semiconductor, because it was famous, the gallium arsenide, department of gallium arsenide. And for your information, some of the students that are hearing me, when they ask me if I know what is the gallium arsenide, I said that's something like germanium. And when I asked that epitaxy reactor, for me, it was atomic reactor. I never heard about the epitaxy or MOCVD. It was, for me, it was the really Chinese language. No way. But only I mentioned one thing. When I saw with my background that I had, I said that, all right, only I know that if anybody can do something for this kind of thing, I can do at least as well as. So for your information, I was fascinated by the semiconductor lasers. How is possible that light is coming out from the tiny things? So 3 months later, I tried with the emissivity that I didn't know what does mean to make the first 1.3 micron lasers. And that is changed really the telecommunication, because that it was the basic to have the DFB, distributed feedback, 1.3, 1.5, or to have the detector for the telecommunication, and they were doing with the liquid phase epitaxy, that it was some problem. So that it was the way. Again, I changed so that everywhere they wanted to have me, that finally Northwestern sent this picture, and the dean came 2 times in France, and they were building over this lake, the building, and say that if I come, they give me the last floor of the building. So that it was after my experience in Paris and at Thomson Central Research Lab, that when I was doing something, some material for the lasers or for the detector, I have to wait in another group. They do the measurement for me or the fabrication, because that it was for the problem. I cannot say that the political problem of the industry and that. So I came and I tried to create exactly a kind of facility, but you have to know that there is no money neither from the university nor from the government, nothing. Everything I did with my own consulting, and the money that I work and to have that for the consulting. But I knew one thing, to put that multidisciplinary, because I was fascinated by artificial eyes or focal planar rays. In France, it was lasers. Here, and unfortunately, when you go to get focal planar rays, now in Turkey, you are doing a lot from the different spot. And my first student, Cengiz Bezishki, Professor Cengiz Bezishki, that you know that he is doing great at the same time, all of you. But everything was really the classified in the hand of the big company, and there were no question at university anybody can come and to make the device. So that's the reason I put together as a multidisciplinary, and I put the name Center for Quantum Device. At the time, nobody could understand. You can see that 30 years ago, what does mean? But from the theory, material, characterization, fabrication, measurement, up to the system, everything at the within the same, and with who? With the genius student, most of them exactly as you know. There's a John Byram that he's here, David Cengiz, and at the same time that we make. So today, what was the situation? I tried to use really the T5 from the optoelectronic, from deep UV up to terahertz. Why? Because for the reason that I explained, and I'm telling you, and all of you, you know, it is, and is continued to be always the material of choice, because we need for at any, and there are the different gap, we try to fill all of the gap from the X-ray up to the really the gigahertz and the millimeter. Anyway, we need to have really the detection, detector, and at the same time emitter. Why? Because all of the different molecules in the brain, in the body, in anywhere, they have a vibration energy, that this vibration energy is between the X-ray up to terahertz. And if you have a kind of lasers or emitter that you can detect that with the detector, that is the basic of the information technology, including that we are going to do, as an example, the quantum computing, that you see that playing with the spin of the electron. So that today, my talk for you is that it was trinitride, now the gallium oxide. And my hope is with your group, especially Professor Ekmel at the same time, to see that really how rich is this subject, and how useful is for the future. So here, what I did again, because I didn't accept any the administrative job. They wanted me immediately, as you can imagine, to be chair, to be dean, then nothing, because I wanted to have exactly to create the center. So that's the reason they gave to my center a kind of the institute that is like a department that has to let me to do exactly the work that I want to do. So I created, instead of department of the solid state engineering that they wanted me to do, I did that solid state engineering within the department of electrical engineering, computer science, and now is a ECE. And all of the course that you can see, I created one after each other. And today, again, the great professor, one is the student of the Professor Ekmel, another is a student of the Dansui Nobel Prize, another one, my own student, Professor Huma Mohseni, that they are teaching, and the Pedro Khalili at the same time, they're teaching. But you have to know that I created the textbook, this emulsivity challenge, that is very, because this one, that's the world first for superlatives of the indiophosphate gallium indiomasonate. And this one, the fundamental of solid state engineering, that's the fourth edition that came out the end of the December. And that you have to know that here, Springer, last year, near 2 million chapter is downloaded. Can you imagine that for the, but one of the things that I would love to encourage, again, that's the mystery of carbon, that is a very small, but that I'm showing that really everything that we can see, for everything that we have is from carbon. You come for the polymer, you come the liquid crystal, everything. So that's the future. Now, coming to the application of UV quantum device, that your group, Dr. Ekmel group, you are the pioneering and expert. Everything that you can see, there are many different applications, but the most important part, I have to say, that is the biofluorescence imaging and the chemical biological agent detection. So for that, if I come, we started immediately when I came to Northwestern. Immediately they called me from the DOD government, and they said, if you can do aluminum nitride. So I tried to develop this reactor with the extron and for the emulsivity, and that to have the gallium, indium, aluminum, and ammonia, and that to use that for the nitride. That is the result that you can see, and some of it, that's the PhD of the professor, John Byram, and that I'm not going to that. So we demonstrated all of it. But one of the important things is that, look at here, because the material growth, it's so important for anything, and especially we were doing for the aluminum nitride, gallium nitride, we have not any substrate. Despite that, 50 years, everybody working, nobody can make substrate of the gallium nitride or aluminum nitride. So we use sapphire, because sapphire has similar the symmetry as gallium nitride. It means that it's wood salt. If you can see here, the growth of the aluminum nitride on sapphire, every 9 plane of sapphire is equivalent to the 8 of aluminum nitride. If you can see, every 9 plane, we have 1 edge dislocation. The rest is perfect. It means that if you have, that's a substrate, and that is the epi layer here that you can see, and there are the area that you cannot have any defect. So you can make any device on this material, and now we came with the UV LED and at the same time the detector, and that is the result that you can see again on sapphire. That's the detector that they gave my student. They were with the contact with Professor Ekmel, if you remember, that it was 25 years ago, if you remember exactly. And by the way, this result, it was the Daniel Walker, that she is not absolutely, she is not the vice president of Global GE. And that it was the result, but the important was the following. We had the LED and we had the detector. So at the time, it was the problem of the anthrax. And if you have a few molecules of anthrax, if you shine the 280 nanometer LED, you can have the fluorescence. And if you have the fluorescence of the 356 and you have a detector similar, the same wavelength, in this case, you can detect a few molecules of anthrax. That it was the subject that the DARPA put, and it becomes a BAA that we're working. And after that, we came at the same time to do 265 nanometer, 254 nanometer, and all of that. It was for the first time in the world. Nobody could believe that is possible in this material to have really this kind of the. So we did that, the first biological and chemical sensor. That it was very important, exactly as you can see here. Now, why gallium oxide? Professor, please follow me. Here, as you saw, UVC light deactivates the DNA of bacteria, virus, and other pathogens, and thus destroy their ability to multiply and cause the diseases. So exactly as I mentioned, many biological agents fluorescent when excited by UV light. By combining UV emitter with UV detector, it becomes possible to devise a compact system that can rapidly detect and identify certain biological agents based upon their fluorescence signature. So here, with the gallium nitride, aluminum gallium nitride, we can come up to UVC, 280 nanometer and 280 to 350 nanometer, etc. But unfortunately, we cannot go beyond gallium oxide based material. That is the one that is coming and to help for that. So that is the part of the future. Now I'm going to explain why it's so important. If you looked at just last year, when I was giving the review for the Air Force, and they asked me, and I explained that is important for the detection for the COVID and at the same time the COVID-19. Immediately after that, 28 January 2021, NISHIA come to say that the new 280 nanometer deep UV LED eliminate up to 99.99% of SARS-CoV-2. And immediately Seoul, they came, show that the violet, it means that UV LED, provide 99% surface disinfection of COVID-19 Delta variant in 1 second. So all of that you can see more and more UV LED, they demonstrated that can really kill, disinfect the bacteria of the COVID. So that is excellent starting again for to come with something more useful, because nobody knows better than Professor Ekmel how difficult it is to go for the 220 and 200 at the same time LED and at the same time the detector, really with the nitride, and you have no substrate. Now we are coming to the functional metal oxide, gallium oxide, that is polymorph. They are like all of the perovskite, they are polymorph. They have different phase that is coming as function, and the change of the different phase that I'm coming, that is the huge subject of the really research, that they showed that the beta gallium oxide that has the structure of monoclinic has the direct bond gap and the wide bond gap of the 4.85 electron volt, has large dielectric constant, has high breakdown voltage, and at the same time the high mobility, exactly. But one problem, thermal conductivity is not good. So they try to use another very important part. For the beta gallium oxide, we can have beautiful lattice match substrate. At the present time, there are many different groups in the Germany, in Japan, in United States, they are doing, and the Notre Dame, and the same time they in France, that the substrate, and they can have 2-inch substrate lattice match in the paper for the beta, the gallium oxide. And that is demonstrated already, that the high power and high voltage capacity gallium oxide can give much higher breakdown voltage by comparison to silicon carbide, gallium nitride, or silicon. And at the same time, they are the lattice match substrate at the same time for the gallium oxide. And if we look again, the Baliga parameter, that is one of the parameters that is important for the transistor, in the case of the gallium oxide, is much better than gallium nitride, silicon carbide, or silicon. So that all of that, exactly, not only that, because each phase has different symmetry, that each of them, they have some, again, at the physical properties that I'm giving. One, the copper phase. The copper phase is a wide direct band gap, 4.8 electron volt, but able to tune its band gap within the UVC region through the various alloys to do with the indium or the aluminum, but they has the unique characteristic of the ferroelectric behavior, that is larger spontaneous polarization, about 3 times larger than aluminum nitride, and is the orthorhombic symmetry. So many different applications that you can imagine and you can give for the future. Now let me to give you some theoretical background. The functional metal oxide of the gallium oxide, we can, if you look here, you have band gap as function of average bond length. All of you are perfectly at the where you know the aluminum nitride, gallium nitride, indium nitride, but without to have any lattice match substrate, you are using with sapphire. But if we come now to the gallium oxide, you have aluminum oxide, much higher energy gap, you know. You have alpha gallium oxide, beta gallium oxide, and at the same time, indium oxide. So by doing the atomic gap engineering the same way as we did for the aluminum nitride, gallium nitride, if we do here, we have much better, again, the area that we can make the real, the useful optoelectronic device. But what is the problem? The problem and the substrate, exactly as you can see, gallium oxide substrate, that is the price at the same time for the 2-inch diameter. Exactly, you can have the price is not as cheap as gallium oxide, but as sapphire. But again, as you can see, you can have it, you can buy it. No, but what is the problem? The problem is the following. Similar to gallium nitride, aluminum nitride, this material you cannot dope with the p-type. You have n-type, that's the difference group. No, they are much more at the same time. That's the result is the 2 years old, but that with the difference technique on the different substrate and that is this result that you can see. That is all recent results for the some special the structure that I cannot speak today for you because I'm just taking the patent for that, and I send it to maybe a university for that. So you can have really for the n-type, you can have great results for that. But the important is how to make p-type. That I am asking and insisting, Professor Ekmel, with your group, you have to work on that, because that is, we need the genius group from from Turkey, from your department, all of you from the physics and
I promise we will do it.
And believe me, that is the multidisciplinary. It's not only material, it's not only physics, it's everything. So please look at that application. It's not new. Because in 2007, at the same time, as you can see, they did optoelectronic device, electronic device at the same time. They used the difference, again, the alloys, everything. And just recently, they are using, again, much more the two-dimensional and to make the transistor with the to make here beta gallium oxide with the 2D material, and to come to combine with the nitride and the graphene. All of that is more and more is a very, very hot subject at the present time. So I want now to give you very short, again, presentation to say that how, what we did, what is our work, and how we try to demonstrate the world first p-type gallium oxide by using, again, exactly the result that I'm going to show you. And that the paper just came yesterday. And that I sent a copy to you and the Professor Tolga. I don't know if you received or not, but it just came. So I'm going to explain to you. So just for your information, because my daughter in the Innovation in Paris, they are using the gallium oxide, but with the PLD since 10 years, and they have excellent result. So it was 2-3 years ago, one of my program managers, the Professor, the Pavlidis, that maybe some of you know, originally he's from the neighbor of the Turkey grid, you know that. He called me because he was at Thompson at the same time. He called me, said that, Manager, can you do the gallium oxide with MOCVD? And I didn't know what is the gallium. I knew that because, okay, we were working that. So immediately in the reactor that I showed you, that we were doing the gallium aluminum nitride, I put immediately the deionized water. Immediately. And using deionized water with the, again, trimetal, the gallium, try to come the result that I'm going to show you. First of all, we try to use the hydrogen as a carrier gas, and to use the sapphire as a substrate, and to do trimetal gallium, again, exactly with the deionized water. When you do, again, the growth, as you know, in any material, the growth temperature has to be approximately 2/3 of the melting point of the material. So we tried to come, because it was nothing in emissivity for the, again, the gallium oxide in the literature. So that immediately we came to optimize as function of temperature, 610, 650, 690, and to do, as usual, the variation as function of the growth temperature, variation as function of the growth rate, and at the same time with the 6:3 ratio at the same time. So, and to see the SEM and AFM, as you can see, for the 690 and 650, very nice X-ray, exactly at 690, with the growth rate approximately 10 to 15 the angstrom per minute. Okay, so that it was the normal, and we tried to do the photoluminescence, and exactly as you are familiar with the gallium nitride, aluminum nitride, the yellow peak. Here we have the similar, but we say that, okay, blue, the blue peak, that's the photoluminescence as for the difference, the difference growth, the temperature, and here for the as function of temperature, and show that this yellow, this peak, the impurity, the defect that we have is very similar to the exactly the things that we had in the aluminum gallium nitride. So we did a lot of study on that, but the most important part, it was the transmission, for to know about the energy gap. So we did again the variation of the transmission, as you can see here, from the 690 to 610, the energy gap didn't change. It's between 4.83 electron volt, 4.75 electron volt. You see that is a very, very little change. But we did immediately with the transmission electron microscope for to have the ideas about the symmetry, because the symmetry is very important. And that it was interesting, again, is at Northwestern, Professor Dravid's group, and that they showed that the first, when we are growing sapphire substrate, first we have alpha gallium oxide, and after that it becomes copper gallium oxide. And that is what they publish again, this paper publication information is there. And that it was, we did immediately the MSM, because that is the easiest way to understand what is the really the cutoff and the energy gap. So we saw that, yes, it's 261 nanometer, and the external quantum efficiency 41.7 at minus 2.5 volt. We did many difference all the time, and that it was the result that we got. But after that, something that was important, because we learned from the experience that we had for the aluminum neutron. So I said that, all right, everything that you saw in the characterization, it was, we were doping at the same time with the silicon, but the material we had, no material was resistive. It was impossible to have any electrical results. So I said that, okay, let's do the annealing. We did annealing at 1000 degrees for 30 seconds. And that I did two ways. Annealing in situ and annealing at the same time ex situ with the rapid thermal annealing, the way that we do for the gallium nitride, aluminum nitride for the p-type. And that, interestingly, we saw that after annealing, here you have the X-ray, that is the red is the after annealing, and the blue is the as grown. So after annealing, it changed the symmetry to become beta. So we give again with the transmission electron microscope, yes, it's become beta. And now one interesting thing at the same time, it becomes conductive. We can do now the measure beautifully the conductivity. So we make a transistor. And as you can see here, as this material, thermal conductivity is very, very low, only 150 nanometer gallium oxide, and with, of course, with the silicon, exactly as you can see. And that it was the result that we published again in the applied physics letters. And the beautiful result, it means that with the 150 already on off, it was more than 10 to the 11. And at the same time, the breakdown voltage, it was more than 350, 400, that the limitation of our system. But our objective is first p-type, not the n-type. So we, first of all, we demonstrated, yes, we can dope with the hydrogen as a carrier gas and trimetal gallium, and at the same time water, we can have the gross and ease the copper phase without any electrical that resistive. When we increase the temperature at 1000, if the annealing, it becomes beta phase and it becomes conductive. That can give the noise transistor. Now coming for the p-type. When we were growing this material, as you know, we have a variation as function of the difference parameter. Carrier gas, instead of hydrogen, to use nitrogen. At the same time, to do the doping, the with and without doping, and to change the 3:5 ratio. We find out when we do exactly as I explained, when we do in situ or ex situ annealing, we have copper to the beta phase. But we found that if we come and to grown under the nitrogen carrier gas, in this case, when we annealed at 1000 degrees, it remained copper phase, and we have a stable copper phase, no change. But with the nitrogen, at the same time, the growth rate decreased a lot, because we know that to send the nitrogen to the organometallic is not very, again, efficient. And we found that if we dope the material with silicon, we can have the conductivity, not only the conductivity, but if we change the 6:3 ratio with silicon, we can have p-type, exactly similar to the silicon in the gallium nitride that use the amphoteric behavior to go one part or the other part. So by that, we try to come and to say that, yes, when we doped with silicon and with the nitrogen as a carrier gas, the material, and they decrease the 6:3 ratio, in this case, we have p-type, again, the transistor, very nice result. So we send again to the one part Pavlidis, that is the expert in the transistor and to send to the Loborton, Professor Loborton at the University of UIC. That is again the perfect, I believe that most of you know him, the theory, but the expert in the transistor. So all of that, and the professor, the Professor Matthew Grayson, that he did with the setback, setback effect, and at the same time with the Hall measurement to show that is a p-top. Professor Khalili, he did again the difference, the characterization to demonstrate that is p-top, and that we saw, and this paper, as you can see, just came yesterday, and that here is the exactly, that is this result that show that yes, we can do the p-top, but how to do the 6-to-3 ratio again with the doping with silicon by using the nitrogen as a carrier gas at high temperature to be the copper phase, and at the same time to make exactly very thin layer, because here is only 100, I believe that is 100 nanometer, very thin layer, because that is one of the beauty again of the system. And that when we did that again, another problem, we gave it again the professor, the George Schatz, that he's the excellent theoretician at Northwestern, and I asked him, his group, to work and to demonstrate, and they work on that, and they demonstrated, yes, by the silicon, if we dope with silicon, and at the same time, the copper phase is much more adapted for the p-type, and at the same time, that is the vacancy of the gallium that is coming with the hydrogen, and at the same time to give the p-type by substitute silicon in the oxygen. So the paper again came out, and if you have a question, I can show you again later. So in conclusion, it was no to say that let's do band gap engineering. Why? Because if the gallium oxide, if I change the 6-to-3 ratio with the silicon, if I dope, if it's really is the silicon responsible, by using the indium, I have to have, again, to have better the p-type. So we did indium, but with the surprise that we had, similar to aluminum gallium nitride, indium cannot go in as a alloys. We change from the 30, 60 difference value, the gap doesn't change, but give better performance. It means that by doping with indium, we can have now the n-type, and the quality it becomes much better. So indium plays similar the way that he was playing, in aluminum gallium nitride, a kind of surfactant. So by that, we tried now to come again by indium without to dope with silicon. We say that no question, anything that we do is n-type. And we make the transistor, again, as you can see here, the transistor to make with the 100 nanometer, and the transistor showed that yes, that is n-type. But no, when we doped, again, without silicon, is always n-type. But if we doped with silicon, in this case, it becomes immediately p-type by changing the 6-to-3 ratio. And that, by that, I would like to conclude here to say that, yes, we can have high quality gallium oxide with MOCVD on sapphire substrate, because we did on the different substrate, including the beta gallium oxide, but you don't want that, because as the thermal conductivity is very high, and the device that we would like to do, we would like to have no substrate. So in this case, you can have the beta phase, you can have copper phase, you can have p-type, you can have n-type, but unfortunately, when we do the silicon as an amphoteric behavior, silicon play as a double donor. It means that is associated with the defect. So still, it's not easy to have the PN junction and PIN on the same material. So we can have separately n-type, separately p-type, but still they are a lot of work to do in order to understand, first of all, p-n junction and the p-top in this material, and this phase change, because each phase has the different properties and needs a lot of work to be done. So in conclusion, I would like to say that, again, we need a lot to understand this material, the physics of the behind of this material, from the phase change, from the, again, the nature of the difference carrier gas, nature of the difference doping, and you have to know that is a very hot subject at this time. There are many different groups that are working on that, but I don't believe that if your group and you try to do that, you can have much faster and to bring really some insight on the project. So by that, I would like here to stop and to say that, okay, to give that if you have any question, I will be very happy to answer.
Okay, Professor Razeghi, thanks for the excellent talk. It was very nice. Especially the first slide, I think you spent 15 minutes, but it was like a brief history of quantum mechanics. It was really nice to listen to it. I will be the first one to ask a question. Actually, I have 3 questions in that sense. First of all, coming back to gallium oxide, I understand that 2 applications seems to be dominant: optoelectronics and electronic transistors. Which one do you think is, will be the future? That's the first question.
Yes.
Second one is about, looks like gallium oxide has a lot of, I would say, nice properties, but what is the disadvantages? Actually, this is also part of the research, I understand, as I see it. And the last one is, I understand that you grow this material in your gallium nitride system, right? And do you foresee maybe another MOC system that's tailored for this material? So many questions, but please go ahead. 3 questions.
Yes, excellent question. All of that, they are very important. The first question that you have, in order that is about the defect. Am I right?
Yes.
The defect.
Mm-hmm.
Yes.
It's the second one.
No. It was
the first one.
Application. Which application? Okay.
Application
the first is which application. At the present time, the best application is the electronic. High power transistor.
That's what I understand too. Yeah.
Absolutely. High power transistor, and that is really very, very important. Mm-hmm. So for the high power, everybody needs, everywhere they need, and you saw the application background. And that, the beauty is you don't need to go to gallium oxide substrate. Mm-hmm. The sapphire substrate is excellent, because that is related to your second question. Mm-hmm. Okay. Sapphire substrate is excellent. But the problem for your second question, for the defect, you know that the lattice mismatch between, again, not only the lattice mismatch of the material, but as I explained, this material beauty is the thermal conductivity is very low, but you need very thin layer. So you don't need the thick layer. And as it thin, in this case, the dislocation can be really very low. But I have a solution for you for the dislocation, similar to all of the other 3-5 aluminum nitride, gallium nitride, by doing the superlattice, thin superlattice of the indium oxide, gallium oxide. That is in the publication that I put that here. You have that, we describe that. When you do that, in this case, the best way to understand the problem of the dislocation and the defect, the first is the mobility. To measure the mobility and SEM AFM. We gave already for the transmission electron microscope for the difference, and that we gave for the difference group. As you know, you have to wait a lot in order to have the results from the really those that they are doing the transmission electron microscope for the defect. I am requesting at the same time, no, begging, if you have in your group and in the in your department, if you have the facility for the transmission electron microscope, I will be happy to send you the material, the difference material, in order to see that the dislocation. But as you saw already, I showed you here is very answer. Yes, here. They did exactly as you can see here, the interface, because you have to be very careful with the result of the TM. They say that the best expert of the TM say that if you give the same material to the 10 different experts in the TM in the different group, you never can have two results exactly the same. But so that is the reason at this time, I cannot tell you exactly the number of the defect, because we are far from that. And all of the device that we demonstrated is the defect density has to be at least 10 to the 8 to 10 to the 9, similar to the aluminum nitride, gallium nitride when you put on sapphire. But the beauty is, as is wide band gap, you know, so a wide band gap material, so that is one of the big problem at this time, is the changing of the gap. You don't know which symmetry you have. And that is the big problem. No, it was the first time that we came to demonstrate from the kappa to beta, only by X-ray. And after that, to give to the microscopy and to say they cannot, at this time, they cannot give us exactly the number of the dislocation, because the difference growth that we do, they are the difference, you know, is not at the present time to say that we understood one and we do exactly that, and to say what is the number of the dislocation, but has to be high. That is the answer to your second question. Now, please repeat the third question.
My question was, you are using a system that's designed for gallium nitride materials. I was wondering if there is a need to tailor those systems, MO systems, for gallium oxide.
I will tell you that it was one of the big problems that we have and we are thinking, because when you have aluminum gallium nitride, oxygen is a problem. So when you put hydrogen, water, and now we try to have absolutely, you have to use at the same time the oxygen or the N2O as a source. But as a scientist, you know perfectly, the growth is at very high temperature. So it doesn't matter, because when you are at very high temperature, that oxygen cannot affect aluminum gallium nitride. And for your information, there are some results that we have that I cannot exactly, as I mentioned to you, the new result that I cannot speak now because I'm taking the patent. So no, there is good news for you. You can really to put this material together without to be afraid about the problem of the oxygen, because that is at high operating temperature. So they are really very nice and beautiful, scientific, it's so rich, this system. And exactly, if you grow this material at low temperature, gallium oxide in the alpha phase has a peak, very nice at 250, that they say that is the excitor, that's a photoluminescence, beautifully to start. So we don't know, we didn't start yet. So each phase and each part has a lot of interesting. But if you have the possibility, if you can do electron spin resonance, that is the best technique for this material, because you can have with the fine structure, hyperfine structure, super hyperfine structure, you can find exactly the problem of the defect, the symmetry of the defect, the place of that, all of that. So really is a starting. So I hope that I give you some.
Okay, thank you. So I should ask the audience questions. Or maybe I ask one.
So okay. Okay, I'm looking on the screen. Is this a single
crystal that has different phases on top of each other right now on the screen?
Is an excellent question that you are asking, because that is always
He's my
problem.
son.
And the problem is it's single crystal or the polycrystal. All right, that is single crystals. Absolutely, because that they showed that beautifully, exactly as you can see, the alpha kappa. Yes, and I have at the same time the detail of that. Look, please, in this paper. All of the answer is yes, is the single crystals.
So can we say this is a well-merged polyphase single crystal? And the upcoming question is, can we locally anneal these? Because you use annealing for phase transitions. And can we locally anneal this structure?
Locally anneal. Yes. Unfortunately, no, because we put that the locally anneal, because that you know you have to have the very special system in order to go. No, we cannot, because we put that we go the whole crystal, whole you know is a 1 square centimeter as an example. So that we do in situ or ex situ under the hydrogen, nitrogen, or at the same time. So we don't do that. We cannot do the local. Why you are asking for the locally the annealing? For to be sure that if we can have, for example, the phase transition between kappa and beta to have parallel at the same time. Yes.
Okay. My idea was because you said if you have alpha or kappa or beta grown under different conditions, their temperature stability differs. So I was just thinking maybe if the top layer is more resistant or less resistant, maybe it would be possible to. What I understand is these are different phases, like alpha, beta. I don't know exactly what they are, but if one is more resistant, then you can locally anneal and like melting cheese on top of.
Okay,
bread.
I explained to you what we did, and that one of my students, especially the Junhee, did. We tried to grow beta gallium oxide. It means that when we are growing is copper, but when we anneal under hydrogen, it becomes beta. You are following me? Okay. Now, in situ, we grown at 690, and that is copper. We increase, we do annealing under hydrogen, again, that the course that we do, up to 1000, it becomes beta. We decrease the temperature, and we grown exactly in the same condition, and that we have, we have copper. And X-ray beautifully show that we have copper and beta together, one on the top of the other. I don't know if I have here I can show you, because I believe that I have here the spectra that I can show you. Yes, look at. Yeah. Here, exactly, no, it's not this one. Yes, exactly. Look at here. It's a beautiful. We have here sapphire substrate. We grown gallium oxide, silica 1 micron beta, and after that 400 nanometer copper. That is the SEM. Show that again. Transmission electron microscope. That is the beta. That is the copper, and beautiful X-ray show that yes, that is exactly as you can see. We have copper and beta beautifully. All right. Yes. And that is a very nice result at the same time. You know, they are very beautiful things at the present time. There are so many. You cannot imagine how rich is this system and what you can do with. Again, that is there are a lot of, you know, nice result. If I go again to here, this one that you were asking exactly the question about that. Absolutely. So exactly, but it's a very nice, you know, analysis, because for that you have to expert. The person that he did here, the group, it was great scientists, material scientists, because as you can see beautifully, you go from each step and you can see the change of the phase. Why? Because in general, for the epitaxy, everything that you do, you take exactly the symmetry of the substrate. You go up. So here, alpha aluminum oxide immediately is alpha gallium oxide, and after that is go to the copper. And that is the transition step by step, as you can see. And now answer maybe to the question of the Professor Ekmel at the same time, the number of the dislocation, and that they have that they are a lot of, in this paper, a lot of results to show that what is really, but to say that exactly what is the number of the dislocation, that is not clear. Okay, so I hope that I answered to your question.
Okay, I cannot resist to say that the way that you explain, you sound like a Michelin three-star chef, French chef, I should say. The way that you prepare the materials. Actually, you are the three-star Michelin three-star scientist in our area. So, again, one more time for the excellent talk. Maybe I see John. I don't know, John. Do you?
John,
can say
yes.
a few things if he hears.
Yes, hi, Professor.
Good.
Professor.
Good morning.
Good morning. Good morning. Yeah, I was going to ask a question as well. So
yes, my dear, ask the question. Yeah,
my
you know, all of
is,
you have to know that is my genius. Exactly. That is the one that he got the award of the Boeing. Boeing give one award in the world to the best PhD. That's something good for the Boeing, and this guy is one of those. Yes, my dear. What is your question?
So my question is more about the future, and when you said that these topics are going to continue over the next 50 years, right? When you look at your career and let's say the ideas that you come up with, what do you advise young students, young faculty, such as myself as well as my students? How do you see them coming up with good, useful ideas? What's the magic of identifying a good idea, such as making a gallium oxide with water? Like how does that process works in your career, or how can you advise us? We initiate new ideas.
You are again. That's an excellent question, because it was in my career. Why I did the nuclear physics. They said, okay, I had the radioactivity go. I went at the physics and all of the, the theory, phase transition. One Nobel Prize came out, but everybody was asking, what's the application? All right. So when you do the theory, when you do that, all of the, high energy physics, how many possibility you have? But when you are doing exactly the fundamental, the material, and for the application, and we need at any time, because it's like air and oxygen, every day, everywhere, we need, again, the material. We need transistor, we need lasers, we need detector. Everybody needs. So for the generation, all of the people that we are in the physics, and especially with the Professor Ekmel's group, and you're at the same time, the things I explained to you when I came to this university, to Northwestern, I tried exactly to come with the quantum device and the material. Nobody could understand what that means. 30 years later, here at the Department of ECE, they tried to change now to put quantum inside of everything. But today, everybody went, you have to know that something that I explained to you, you are young, but I became 1988, when the Benders and Muller, they got the Nobel Prize on the HTC. It was the year that I got the IBM Prize of the Science and Technology for the emissivity, the 1.3, 1.5 micron. Every group in the world, they tried to transit and to go to do the material for the EBQ for the HTC. all of the difference grew. And when you were going to the paper of the applied physics letter, everything, the number of the semiconductor was done as a 1%, and everything was at all of the meeting from the 7 o'clock in the morning up to midnight, everybody was coming, they tried some element. 15 years, 20 years went on, nobody did anything, came back, but now again the 3-5 and semiconductor, it becomes important. As you know, in United States, at NSF and all of the DoD, they put now all of the energy, effort.
Billions and billions. Now everyone is talking about semiconductors.
Exactly. And everybody now is speaking about the, again, aluminum nitride, gallium nitride, all of the subject that I have in my group at the present. That is the things that 30 years ago we were doing. So my answer to your question is always teaching your student and yourself something that is useful. And nothing is more useful at the present time than the really mixture of the 3-5 with colon 4. Because 3-5 is the direct gap, covalent, and at the same time is the zinc blend. So for everything, we need the detector, we need focal planaries, we need lasers at any wavelength. And this system yourself, when you did the gallium nitride, gallium aluminum, gallium indium nitride, aluminum nitride, look at that, the result. After now everything, it becomes hot and important. And note that the reason that I brought the gallium oxide, because this system is very important for the transistor, and at the same time, if we can do, again, the LED, if we can do the really the P-top and the C. And now you are going to that, I believe that immediately the Professor Özbey is going to do it in his group immediately to combine again the trinitride with that and to come with the exactly to do the, because detector, you can do excellent detector in gallium oxide. And as you know, if you look at to do the literature, you can see that they try to have the gallium nitride and to do the gallium nitride at 2000 degrees and to come under the oxygen, the pressure of the oxygen, and to replace oxygen by nitrogen and to have the P-top gallium, the gallium oxide. So they are the differences, but is the reach. So my advice is really, that's the reason I came to this subject exclusively because it's rich and it's future. So I hope that, John, at the same time, I want to have the kind of collaboration, really, because at this time, they are a lot of, you know that Ali Sair, that's his program for the gallium oxide is he's supporting from the India, from Europe, from China, from everywhere, and that is the
even Turkey.
I loved and the Turkey at the same time. Absolutely, yes, even in Turkey, exactly. So that is and is a rich subject, you know, because for me, as I did the phase transition in the perovskite for my PhD, you know, and that is it's so interesting to understand the different phase and the transition between each of them, and to understand the doping, because that's the similar problem of the gallium nitride. Professor Özbey, how long you put the effort for the P-top of this material? Because that it was the subject of John at the same time he did for the gallium nitride. How many years and how much effort you put for that? And at the same time, similar problem we have now with the gallium oxide. All right, so it's very rich and needs the great people like all of you to have passion and hardworking. All right, so that is okay. So my advice, please keep going with the material, especially semiconductor and the 3-5, and at the same time because that is still in 40, 30, 40, 50 years, everybody needs. Okay, from the material, characterization, fabrication, and etc.
So,
okay, maybe I should leave the final word to our chair, Tolga.
So I'd like to thank Professor Razeghi for her excellent talk, and for even someone like me who's an outsider to this, it was very exciting to hear and see the applications in communications in particular, in my case. And thank you for the wonderful talk. Thank you for the wonderful advice for young researchers, for, I guess, mid-career researchers as well. And we appreciate that you took your time and spent quite a bit of time with us. And if after hopefully the pandemic allows, you have an open invitation to visit us in person as well. So if you'd like to come to Ankara at some point in the future, we would love to host you here in person.
Thanks a lot. Again, the same invitation for all of you. It was great again. And I hope that we are going really to continue to have a lot of connection and a lot of collaboration. And at the same time, please come and send the best to me. And all of you are the greatest, absolutely. And all the best. And I wish the happy holiday and happy New Year's. And please take care and all the best. Thank you again.
Same to you. Happy holidays and happy New Year. And,
thanks again. Thank you.
Okay, thank you. Thank you, Manish.
Thank you again. Bye-bye.
Okay. So good evening, everyone. And good day for you in USA, I think I should say.
Perfect.
So I hope to see you face to face sometimes in the future.
Perfect. So,
okay.
Bye-bye.
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 End of our seminar. Thank you.
Thank you.